So I is a set which is not equal to 0, it's a subset of S. One can easily verify that this I is an ideal of S. One can easily verify that. It's again simple to verify I is an easily verify that this I is an ideal of S. It's an ideal of S. And it's not equal to 0, therefore I is equal to S. Therefore I is equal to S. So that means every element of S satisfies this property. So that implies for all x in S, Sxs is equal to 0. For all x in S. So which implies S cube is equal to 0, which is equal to S. A contradiction because S is not equal to 0. It's a contradiction. A contradiction. Contradiction is required. So it means that whenever S is a zero simple semigroup, then SAS is equal to S for every A not equal to 0 in S. Now let's prove its converse. Conversely, we assume that for all A not equal to 0, SAS is equal to S. We show that S is zero simple semigroup. Let's prove the converse. Conversely, suppose that SAS is equal to S for all A not equal to 0 in S. For all A not equal to 0 in S. Then you can see this. Then clearly this S cap is not equal to 0. S square is not equal to 0. Is it really true? S square not equal to 0. How? SAS is equal to S for all A not equal to 0. Okay. So for if S square equal to 0, then S cube equal to 0. But look at here. This if A equal to 0, then S is equal to 0. In that case, it's not equal to S. So that's trivial. But A is not equal to 0. So this set. Can I say this SAS is a subset of S cube? S cube, that means S is subset of S cube. So here you can see S is subset of SAS where A is not equal to 0. Okay. Oh, sorry. S is equal to SAS here. So it means that so this is actually SAS is subset of S cube here. SAS, it's the product of three elements of S. So if you choose any element here, so it's of this form x, a, y, and that always belongs to S cube. Well, this is true actually. But this cube is our S is subset of S cube. So for if possible S square equal to 0, if S square is equal to 0, then S into S square is also equal to 0. So which implies S cube is equal to 0. So this is equal to 0. So in that case, our S is equal to 0, which is not the case because S contains some non-zero elements. So that means this S square is not equal to 0 because for if S square is equal to 0, then S cube is equal to 0, and here S cube, S is subset of S cube, which means that this our S should be equal to 0 because it is subset of S cube. Okay, so S square is not equal to 0. That's the first condition for zero simple semigroup. Now we prove it's a second condition. Second condition means that 0 and S are the only ideals of S. So let's choose any ideal. Let A be any ideal of S. Be any ideal of S. and say A is not equal to 0, we show that A is equal to S. It's a non-zero ideal of S. And let A be not equal to 0 belongs to A. It's in this idea. It has a non-zero element. Then you can see this S is equal to SAS, and that's subset of SAS because A is element of A. Okay, but this one is ideal, so it's subset of A. SAS is subset of A, so which implies that S is subset of A. That means S is equal to A because A is always subset of S. So hence if A is a non-zero ideal, if A is a non-zero ideal of S, then S is equal to A. So that means S is only two ideals, namely 0 and S itself. So hence S is zero simple. Hence S is a zero simple semigroup. Zero simple semigroup. So there is a result analog of this result for simple semigroups that you can see yourself. You can see it's actually corollary of this previous theorem. It's at the page number 67 of the book Fundamentals of Semigroup Theory by Hobby. So you can see that. Now let's prove one more important theorem. So the statement is, if let's first define the minimal ideal. Actually, it's related to that one. Let S be a zero simple. Let S be a semigroup with 0. Okay. Let S be a semigroup. Okay. An ideal, let's define it. An ideal I of S is said to be zero minimal. Is said to be zero minimal ideal. Okay. An ideal I of S is said to be zero minimal ideal. Zero minimal ideal. If it is the minimal, if I is minimal among all the non-zero ideals of S. Non-zero ideals of S. That is if J is not equal to 0 is an ideal of I, is an ideal of S, then I should be subset of J. It's a minimal among all non-zero ideals. So for if we take any non-zero ideal of S, then I should be subset of J. So in that case we say I is zero minimal ideal. So that's the definition of zero minimal ideal. So it's a minimum among all the non-zero ideals of S. Now let's have a following theorem for zero minimal ideals. Statement is if M is a zero minimal ideal. If M is a zero minimal ideal of S, then either M square is equal to 0, either it's equal to 0, and if it's not equal to 0, then M should be, or M is zero simple. M is a zero simple semigroup. So that's a statement of this theorem. Let's prove this. So first we assume m is zero minimal. So we need to show that m square is either zero or it is a zero simple semigroup. So clearly this m square is an ideal of S. Clearly m square is an ideal of S. Okay. If m square is equal to 0, then we are done. Then because we have to show that either m square equal to 0 or m is a zero simple semigroup. Then we are done. Then we are done. So assume that m square is not equal to 0. M is an ideal. So this m square is an ideal. Then m square is a non-zero ideal. Is a non-zero ideal of S such that m square is obviously subset of m. M square subset of m. But m is minimal, so this m square must be equal to m because it cannot contain any proper ideal, proper non-zero ideal as m is minimal. So then this m square is equal to m as m is zero minimal. M is zero minimal. It cannot contain proper non-zero ideal. And it contains m square. That means m square cannot be proper actually. So it means it should be equal to m itself. Okay, our m square is equal to m. So this means m cube, which is equal to m into m square, that's also equal to m. This is very simple. Now let's choose any non-zero element. We had to show that m is zero simple. We use the previous theorem. S is zero simple if and only if S is equal to S for every non-zero element A in S. So here we show that m is equal to m for every non-zero element A in M. So if we prove this one, m is equal to m for every non-zero element A in M. So then we can apply previous theorem. We say that this m is actually a zero simple semigroup. So let's choose any non-zero element. Let A be not equal to 0 in M. A be not equal to 0 in M. So then we can see this. Let's look at this. M, which is obviously subset of S1A, S1 because M is subset of S1. That's simple. But S1A, S1, it's actually because since S1A it contains A and it's also subset of M, you can say it's subset of M because M is ideal and it contains A actually. This is an ideal of S and it is contained in M because M is an ideal and A is in M. A is in M. And it's non-zero because it contains A, that A is not equal to 0. So it's a non-zero ideal of S contained in M. It's contained in M. So that means it should be equal to actually. It should be equal to M. So here as S1 is not equal to 0 and S1 is a subset of M. So it's a non-zero ideal and it's contained in M. It must be equal to M. And this M, you can say this M is equal to M cube. That's equal to M, and which is equal to M. That's here S1A, S1M. Because M is equal to S1A, S1, which is equal to M, S1A, S1M. but this ms1 is equal to m, or it's subset of m, in fact, because it's an ideal, so ms1 is subset of m, s1 m is subset, because m is two-sided ideal, it's subset of m, a, m, it's subset of, so that means mam, which is subset of s1a, s1 equal to mq, and it's again subset of mam, so that means this is not actually proper inclusion, because it starts with mam and ends with mam. So that means inclusion is not actually proper, so which implies that this mam, it's equal to, so any element, it's equal to the any set in this chain, so let's choose this one, it's equal to m. So which implies that m is actually a zero simple semigroup by applying by previous theorem. So therefore m is a zero simple semigroup, therefore m is a zero simple semigroup by previous theorem. By previous theorem. Let's define the kernel now. What do we mean by kernel actually? This theorem is very important for a semigroup without zero, because if S is a semigroup, if S is a semigroup, if S is a semigroup without zero, then this S has at most one zero minimal ideal. Zero minimal. It has at most one zero minimal ideal. Okay. If S is a semigroup without zero, then this semigroup S has at most one zero minimal ideal. So for if possible, for if M and N are two zero minimal ideals, then Mn is subset of M, and Mn is also subset of N, because by treating M as ideal, Mn is subset of M. By treating N as ideal, Mn is subset of N. And this is not equal to 0, and Mn is not equal to 0, because as the semigroup without 0, Mn is not equal to 0. So that means this M contains non-zero ideal Mn, because Mn is itself an ideal, and this N contains a non-zero ideal Mn. Both are ideals actually, and they are contained in M and N respectively. Since M is minimal, so that means Mn should be equal to M, and Mn should be equal to M, so which implies M is equal to N. So it is only at most one zero minimal ideal, and in that case it has a zero minimal ideal, a semigroup without zero, then that zero minimal ideal is called the kernel, and which is denoted by K. So it's actually well defined, because it is the unique one, it's called the kernel. So thus for a semigroup without zero, it has zero minimal ideal, or it has exactly one zero minimal ideal, and that unique zero minimal ideal for a semigroup without zero is called the kernel of the semigroup. It's called the kernel of a semigroup. So next theorem, which follows from the previous theorem, that you can do yourself. I will only write the statement here. Statement of this theorem is, let S be a semigroup without zero. Let S be a semigroup without zero. So either S has a zero minimal ideal, either S has no zero minimal ideal, or it has exactly one zero minimal ideal. Now suppose if S has a kernel, means zero minimal ideal. Suppose it has a kernel K, then this K is zero minimal ideal, then K is a simple semigroup. It's not zero simple then, because here we don't have zero, then K is a simple semigroup. It follows from previous theorem. Proof. It follows on similar lines. On similar lines as previous theorem, as previous. So the proof is actually similar as the previous theorem. So that's the end of this section, simple and zero simple semigroups. Thank you.